Good morning, ladies and gentlemen, and most welcome to the session, which we believe to be the greatest savior of sustainability, if I may say, because others are trying to reduce the carbon, but this session talks about exactly capturing the carbon and just putting it somewhere where it doesn't leak. So that way, we all know that may be the most effective way to reduce the carbon. So this morning I am Raman Jha with you. I work as executive director in PwC and have quite a good experience of working in sustainability and upstream oil and gas sector. So I would be chairing the session, and I have very eminent panel members with me who would be speaking on the subject. And just to give you, we are still falling short of two speakers which would join us midway, and as and when they join, we would bring in their presentation. So we have Taibu Sel from as business development manager from NextCam, and he is based out of Italy, while he is here for the session, and he also works in this domain in India. We have Ankit Gupta, who is R&D executives with NTPC, and then we have Ravi Kumar Nithi, who is the CCS integration lead with GE Vernova, and we are expecting Sandeep Gagat, who is industry solution consultant with Siemens, and then Samir Virmani, whom we are also expecting, and he could be here maybe in next couple of minutes. He comes from GAIL, and all these panelists. So I bring to you a combination of people who work on the ground, so you will hear from them the actual ground reality, how it is happening and how it can happen. How do we see the future going forward? So without much ado, I would request Taibo Sel to make his presentation and please enlighten the gathering.
Nice to meet you all. My name is Thibaut Schell. I'm a business development manager for NextChem, which is part of Myre Technimont Group. So you may know the company by the name Technimont. I've been working for NextChem for 2 years. Our company is based in Italy, in Rome, and in Milan, but we also have a strong presence in India. I will talk to you about carbon capture and how it should be optimized capex-wise and to also improve the system efficiency. Okay, so first I will talk about NextChem. I will talk about the model that we did for CCS and the issues that we've been facing, how, let's say, the whole model should be designed, according to us, and then I'm going to talk about a few case studies for the carbon capture. Okay, so as I said before, I work for Myre Group, which is let's say, divided into two smaller groups. On the left side, you have the Sustainable Technology Solution, STS. So NextChem is part of that STS group. I'm not going to go through all of them. I can mention also Stami Carbon, which is working in the field of ammonia and fertilizers. And on the right side of the group, you have, let's say, the EPC part under the names mainly of Technimont and KT. So let's say that on the right, you have the guys that build the plants, and on the left, we have the part of the company that is focusing on our different technologies. So NextChem works on as I said, sustainable technologies that can be then used for the construction of plants. So we have a huge R&D department. We're working on solutions in plastic recycling, in hydrogen, and in CCUS. So I'm part of the CCUS business. So carbon capture now. So we think that carbon capture, and I'm talking here about post-combustion carbon capture, is not that easy because we always think it's just plug and play, but we think that such a plant will actually, interfere with the plant that you want to capture the CO2 from. So where is that CCS plant going to, let's say, bother the plant that is already existing? So of course you're going to have to deal with the flue gas path where the CO2 has to be captured from. Then you're going to deal also with the combustion control system. And then if you want to implement these CCS plants, you will need some more utilities. So I'm talking about steam, water, power. So it's not that easy, and we think that it's not a plug and play solution, at least from this point of view. So what we did is in NextChem is that so we are trying, I will show you first in this slide how this CCS plant works. I'm not going to go through all of the process because I think you are all quite, let's say, familiar with it. So on the left side, you have a column that will capture the CO2 using some amines, and on the right side, you will actually take the CO2 back from the amines in a stripping column. So why are we looking at this technology? Of course, because it's really reliable and flexible. It means that it can deal with any type of flow rate, well, CO2 concentration, and also the fact that the flow rate that you will get the CO2 from is not going to be always the same flow rate and the same CO2 concentration. It's a really reliant model because it can, well, plant because it can deal with a lot of traces of oxygen, NOx and SOx, which are, well, poison also for the amine. So if you have those kind of components, then you have to bring some kind of makeup of amine. It's really effective, as I said, in terms of flue gas CO2 concentration. So it can go from really low, like point something or 1 or 2% of CO2 concentration, up to really high concentration. So it's really also, well, reliable from this point of view. And then it's a well-known technology. So when we have people that are actually coming to us, coming from the steel, from the cement, business. It's not just oil and gas, and sometimes they don't really know what to do. And so it's really reliable and well known, and it's been done before. So this is why we think that it makes sense to use also this kind of technology. And last but not least, since it's always going on, we're making more and more plants, and not just us, of course. So, well, major efforts are made to make it even better all the time. So what we've done in NextChem is that we thought that we need to have a strong model to actually deal with these plants. So, well, the idea is that you shouldn't go straight to the different licensors, but you should come to us before, because we have a strong model. And the basis of this model are two things. We think we should define the type of solution that you will use, because when we talk about amines, we have actually lots of different types of amines. So you can see on the right side, for example, based on the type of solvent that you use, you will have different consumption of power, and the power is actually mainly located on the stripping side. So basically, you need steam to get to take the CO2 out of the solution. And then what type of model should be used to actually, simulate those kind of plants. So we've been using Aspen ISIS, Aspen Plus, and also a different one from Promax, which is called Ryan Research and Engineering, so BRNE. Okay, so the process of capturing CO2 from amines is not that easy. So actually, it's not just the gas gets stuck into the liquid and that's it. Of course, you have different type of reaction that needs to be modeled. So this was part of our model as well. So I mean, I'm not going to go through all of the technical details. I'm happy to talk about that afterwards if you want. But basically, what we did is that on the liquid phase, we are using NRTL activity coefficients, and on the gas side, we are using PC soft, because it's what makes it actually complex is that you have both the liquid phase and the gas phase, so it's not that obvious. And then starting from there, we are actually adding some more of our own, let's say, know-how, because we know that you have also, when you do this kind of plan, you have also when you capture the CO2, formation of different, let's say, other components that needs to be also put into the simulation, which is not that easy. And then we are adding some more, let's say, components of the amine solution based on our own know-how. Again, I'm happy to go into more details afterwards if you want. Okay, so as I said, when you do this kind of simulation, we actually face different type of problems that we then solve. So as I said, you have some different pollutants in the solution. So it's not just CO2 and different gases. You have also other gases, basically, acid gases, so SO2 and O2, that are actually forming salts that will take a bit of the solvent out. So it means the more you form those salts, then the more you have to bring some makeup of amine. So that's kind of a problem. So we are also able to actually simulate those salts formation. Then the pressure is really key as well, because if you're not able to actually simulate the right partial pressure of CO2 in both of the columns, then you are not sure how much of solvent you need, and then on the other side how much steam you need. So it's really, really important to have the right feedback also from the column vendors, so tray by tray, or in the packing, knowing what is the profile of the pressure. So this is key for the whole process to work and to optimize both capex and opex. And then, as I said, but I mentioned it before, on when it comes to the heats of the the steam that you actually use to strip the CO2 from the amine. Here we're also working with the different licensors because this is a key aspect and this is where your main OPEX is. So it's important to have those three steps that are those three problems that have to be solved in the different simulations. So what we did is that we actually created some clusters because, as I said, you can use carbon capture in really different types of plants. So it's like a patient that goes, that goes to the hospital. First, come to us, and then based on your problem or what you want to do, we will actually send you to the right place. So what we did is create some clusters based on the CO2 concentration. So you have the details. I'm not going to go through all of them, but basically, if you have power generation, it's going to be a low concentration, and then you will have cases where you have almost pure CO2 or at least half and half with other gases. So clusters based on the CO2 concentration that will probably have different plants afterwards for the capture. So it doesn't mean that you have always the same type of plant for the different type of plants that you have. And then of course, based on the pressure and based on the temperature, you might want to do also different designs for the carbon capture. So it's important that we know where you come from, we know what type of plant you have, what type of concentration, and then we can actually decide how to size or at least pre-size before you go to the actual licensor. I'm going to close this presentation with a couple of examples. So first, I'm going to mention the steam reformer in the frame of ammonia production. And by the way, here I want to mention that as a group here, and especially here in India, in the past we've built large-scale carbon capture plants. So at the time, it was not carbon capture for the sake of capturing CO2, but it was carbon capture to capture CO2 and actually produce more of urea and fertilizers. So we have a really strong know-how of building such kind of plants, and especially here in India. So I'm happy to be here as well to mention this. So in this type of plants, the steam reformer, sometimes it's not that easy to optimize and make the most of the energy that you have. For example, you have at the stack of those most of the time older plants, the temperature is quite high, which is nice because then you can take this heat and then probably use it to make the steam and to capture, to spend less of OPEX for the capture. What you could do as well, but this is just an example, is that you could also decide on the different, because we assume that you will have different steam reformers. You could quench each of the reformers and then have a single big capture plant. So you will probably save some capex doing this. So you would quench all the different points of emission and then send it all together and mix them and capture just one plant. So but you can just quench it, or you could also bring and implement a system where you would get the heat and transform it into steam and use that steam for the capture. So make the most of the heat that you have, and probably in this kind of plant it would make more sense to have a single capture plant. Then if I move on the other side, so we have the power generation plants. So this is a bit different because in those kind of plants, we know that we have low concentration of CO2, so a couple of percent, so it's a bit of the opposite. And the challenge is that it means you will have a really high flow rates of gas, but a really low concentration of CO2, so you will have bigger plants. But let's say the other type of issue with this plant is that you're not going to have a stable flow rate of flue gas, because in those type of plants we have gas turbine, combined cycle, so it means that the flow rate is going to change from time to time. The CO2 concentration may change from time to time, and you're probably going to have more than one turbine. So the overall, let's say, flow rate that you need of flue gas that you need to capture is going to change a lot, and the CO2 concentration will stay low, but it might change as well. So what would you do here? We think that in that case, and it's a bit different from the case one, you might want to have different capture plants next to the different emission points. Of course, it makes less sense because you would think if I have a big plant, I will save some money because I will have just one plant. But it probably is better because otherwise you will have some turn down issues if you have just one plant. So you might as well have smaller plants, or what you could do is have just smaller plants for the first column. So you would absorb at different places, and then you would actually strip back the CO2 from the in the stripping column in just one big column. So this is also an example of tailoring based on the different emission points that you have and the concentration of CO2. So it doesn't mean that you will have always the same plant at the same size, And this is really different from the case one, because here you would have smaller plants, and then you can decide to mix and having all small plants, different, or having all just one main, let's say, stripping, and the rest of the plants would be separated. So those examples, sorry, show that you don't always need a plug and play solution. And the message as NextChem is that, and as Myra Group in general, is that we strongly advise you to come to us first. Well, regardless of if you come from the oil and gas business, steel, salmon, whatever, we have a know-how for CCS capture and let's say post combustion capture, and we will help you to have a pre-sizing of the plants before going to the actual different CCS licensors. We can tailor the plan for your needs based on the CO2 concentration, the flue gas, flow rate, if you have some fluctuations. And based on this, the CCS plan could be completely different from one case to another case, as I showed you before. And of course, we do also some feasibility study, some, let's say, pre-feasibility also analysis. So come to us, and we will be happy to help you and tailor the plans to your solution to save capex or opex, or hopefully both, and then we can go together to the licensor. Hopefully, we will skip some steps like this. So thank you for your attention, and happy to answer your questions. And I hope I made it in the time. So.
Thank you, Mr. Sel. You made a very insightful presentation. So now I would request Ankit to make his presentation. And as I said, Ankit is a mechanical engineer and works as a R&D executive with NTPC. Has plethora of experience in working with in the CCUS projects, and he would be talking about assessment of CO2 coming out of as a flue gas from the thermal power plants. So over to you, Ankit.
Good morning, everyone. I hope you had a fantastic start of the day. Let's dive into the presentation on assessment and evaluation of CO2 capture from coal-fired power plants. So, I'm Ankit Gupta and I represent NTPC Netra. And currently, we are focused on these topics: carbon capture and utilization, green hydrogen, energy storage, and ash handling. But this presentation is confined to the topics: need of CO2 capture, CO2 capture and its avenues, carbon capture and implementation, carbon capture utilization in a landscape, the need of the hour. We all are aware of the carbon emissions. CO2 level in atmosphere was 280 ppm before pre-industrial era, and right now it's 410 ppm. Global emissions per capita is increased to 6.59 from 6.2, and India's per capita emissions is 2.5 tons per CO2 equivalent, and we are contributing for less than 40% of the world's average. So India is growing as a faster in electrical based economy, electrical based mobility in two-wheelers, three-wheelers, four-wheelers, electrical urbanization and rural urbanization. So we were in 2020 we were at 1004 of per metric ton of per year. Now we are at expecting it to be rising to 1200 ton and 10 by 2030. So CO2 emissions from coal-based power plants are significant and were 62% in 2020 and are expected to be 54% by 2030. In order to sustain coal-based power plants, CCUS is necessary. So CCUS shall play important in Indian context, and hydrogen shall play a critical role in CCUS development. These are the three pillars which are necessary for low carbon transition: renewable energy, green hydrogen, and carbon capture and utilization. We all are aware that India has abundance of coal, around 149 billion tons of proven coal reservoirs, and 319 billion tons of total coal reservoirs. India does not have meaningful oil and gas reservoirs, and bulk of it is imported. Indian economy is also based on, for few states, it's dependent on coal. Jharkhand 91 percentage, Madhya Pradesh 73 percentage, and Chhattisgarh 66 percentage. Employment of nearly 3.5 lakhs to 5 lakhs of skilled, all skill set people are dependent on coal. Financial investments of more than 10 trillion INR has been done on coal-based power plants. So thermal plants cannot be eliminated, and thermal power from coal is the backbone of Indian economy. Carbon capture avenues. The potential carbon capture avenues are, so CO2 synthesized from hydrogen makes Cat1 compounds, which are liquid fuels, methanol, ethanol, dimethyl ether, aviation fuels, and we are targeting in all the streams. Fertilizers, urea, gaseous fuels, synthetic methane, carbon morphology, black carbon, organic chemicals. Cat2 compounds where CO2 can be directly utilized or stored in enhanced oil recovery, food and beverages, human grade CP, industrial usage, economical chemicals, and building products such as carbonates. CO2 implementation. So, coming to the roots of the Netra, we have done all the, we have walked on the uncharted path and the developed, went into physical route, chemical route, and biological route, and done the pilot scale projects in the TRL level of 6 to 7, and found that CO2 recovery from amine based absorption process is around 85%. So let's jump into the project which is already implemented and commissioned in August 2023 at NTPC Vindhyachal, having the capacity of 20 tons per day, that is 833 kg per hour of CO2 is already captured. The plant is running successfully. So let's start. Flue gas is tapped off from after FGD, and it is brought 340 meters away from FGD to a land area of around 500 meters square at a flow rate of 6500 kg per hour. Flue gas is around having a temperature of around 110 degrees Celsius. It is sent to the direct contact cooling column, where it is cooled down to 40 degrees by sprinkling of water, DM water. Further, scrubbing solution is sprayed in the top column of the top section of the contact cooling column, and if there is any SO2 present, that is removed by spraying of sodium hydroxide. Flue gas of 40 degree is sent to absorber section, where the it comes in contact with the solvent and makes a double bond with CO2 makes a double bond with solvent. It should not go off, so the water is sprinkled at the top section and the solvent is brought down. Rich solvent, which has already absorbed the CO2, goes to the lean heat exchanger and exchanges its heat with the lean solvent, which is coming back from the stripper column. At the stripper column, this rich solvent is injected from the top part of the column, and from the bottom part, steam is going from the reboiler at around 3 bar and 190 degrees Celsius to break the double bond between CO2 and the tertiary amine. At the end, CO2 is collected at 90 degrees and it goes to the condenser, and further at the reflex drum, any liquid part in the CO2 is captured, and at 40 degrees we get the dry CO2 of 99.4% molarity. These are the few amines which are available commercially for capturing CO2. We have gone ahead with CDR Max, Carbon Clean. Others are MHI, which has to be implemented at the higher scale, Shell, Console technology. Further, this captured CO2 is utilized for preparing methanol at NTPC Vindhyachal only for 10 tons per day. Other solvents which are available in the market and since 2012 till 2024 are tested at DCM Norway Technology Center Mosgard. These are the results and the findings. So the power consumption with the amine based CO2 capture is around 0.171 kilowatt per kg of CO2. Consumables, tertiary amine was consumed around 150 grams per ton capture of CO2. Sodium hydroxide was used as 30 grams per ton of CO2 capture. Sodium bicarbonate was used at around 4.8 kg per ton of CO2 capture. Utilities, specific steam, which is a major concern, is was consumed at a rate of 1.38 kg per kg of CO2. Specific cooling water was consumed at 0.72 kg per kg of CO2 capture. Specific DM water was consumed at 0.12 kg per kg of CO2 capture. So why steam is a concern? Because generating steam also has a cost. Since we have at abundance in our power plants, low grade steam, it is free for us. Okay, going back, uh, I have shown you the percentage of the purity was obtained at 99. There were 2 dips found during the first day, but later it was rectified. And steam consumption per and with respect to graph is also shown with respect to CO2 capture. So the learnings at the end, process design, handling of residual SOx, as SOx is the main killer for the amine, was most important part, and it was a dual wash column, direct contact cooling, where cooling was done in the bottom section and SOx was removed in the upper section. The plant is operated for more than 10,000 hours. Emergency handling was also taken care. Process improvement is also done. Purity I have told 99.4. Power was 0.17 kilowatt hour per kg of CO2. Heat required, the second concern, is around 300 kilojoules per kg of CO2. Specific cooling load, 3500 kilojoules per kg of CO2. Why this is a concern and how it can be taken care are the learnings. So potential for the improvement is the flue gas based design, where we can already use the heat of flue gas which is going out of FGD at 110 degrees can be utilized, as we are cooling it down to 40 degrees. Next, the integration of the heat pumps plays a critical role here, where when we are using the steam in the stripper section, that can be done from heat pump as well. The rotating disc absorbers are new in the market and can be used to reduce the land footprint area. CCUS in the landscape, what we are going to do next. Okay, we have done 1 into 20 tons per day in Vindhyachal, and we are going ahead for 25 tons per day carbon capture for doing ethanol project. The same scale, 10 tons per day. We are going for 2 into 3, 25 tons per day at Pudimatka, and we are going for again 2 into 650 tons per day plant. That is the future. This CO2 capture from NTPC Simadri will be taken to Pudimatka, and it will be compressed at 150 bar and 40 degrees Celsius. It will be transported. It will be the first of its kind in India. Then CO2 utilization in methanol, urea, SAF. And this model is showcased under the Ministry of Power umbrella. You can visit us. The plant, first of its kind in Vindhyachal. Just a shot of this, and connect to the International Maritime Organization. Why we have gone for methanol? So the rationale why we have gone, because M15 grade methanol can be used as petrol also, with a slight change in IC engines, which has been done by Ashoka Leyland already. M15 petrol engines, tweaking of firing angle. Diesel equivalent, we are using it as LDO replacement in our Vindhyachal. We are planning to use in the boiler. Methanol has high octane number, so the CV is low for it. Base chemical for olefins chemicals like formaldehyde. Market size of methanol is high, 2 million per ton, 2 million tons per year. Domestic production is around 0.2 million tons per year, and import is 1.8 tons per year. So that can be reduced by scaling up the technology. Potential usage in shipping industry, domestic cooking, met fuels has come up with the cooking stoves as well of methanol. Domestic gensets, Kirloskar has done it, and domestic transport, diesel transport. Again, Medfuel is doing the transportation as well. So potential of off-takers of green methanol are international maritime organizations. The need of the hour, establishing full scaled up CCUS plants to reduce the steam and power after the learnings we have from our existing power plant. To reduce the steam is the basic concern, and foster the calibration between industry and academia in the field of CCUS. So what are the enablers for this full-scale CCUS plant? So non-monetary and monetary policy supports from Government of India, which is in the form of GST waiver, green tax, or open access power, which can be utilized for electrolysis process. As of now, power majorly is consumed in electrolysis process in hydrogen generation. Support price for CCUS green products for the initial few years, low cost financial, including VGF support, and low cost RA power. That's all. Thank you.
That's all right. You can take a seat. And now I'll invite Mr. Ravi Kumar Nithi, who leads the CCS. So Mr. Ravi Kumar Nithi leads the CCS integration for GE Vernova in APAC region. Has been an engineering professional for 20 years and has quite significantly worked in the CCS technology. And he would be making a presentation on CCS integration with CO2 recirculation. Over to you, Mr. Nithi.
Thank you. Okay, so I start discussing about where Ankit ended. He was talking about the challenges where we need to reduce the cost and reduce the energy requirement for the carbon capture. So pretty much I'm going to cover on those topics. Just that Ankit covered on the coal-based one, I'm going to touch base on the gas-based power plants with the carbon capture. So before getting into the topic, right, so despite of a lot of skepticism and sometimes a lot of criticism about the carbon capture, there is an undeniable fact that carbon capture have to be there in any scenario of IPCC, whether it is a business as usual or if you're going to the net zero scenario, we have to have a carbon capture. So, but just that is a timing, whether we need to have it today or whether we have to have it tomorrow is what we are working around. And most importantly, the carbon capture as a technology. Basically, the post-combustion carbon capture is going through the vicious cycle. What I meant is, if we want to implement the more carbon capture plants, we have to reduce the cost. But to reduce the cost, we have to, implement more number of plants. So it's just a cycle, and somewhere someone have to break it, and which Thibault covered in the beginning of the slide. So they are working on reducing the capex, and we are at the GE Vernova, we are working similar about reducing the capex and increasing the efficiency of post-combustion carbon capture plants with various technologies which I'm going to cover on it. So that being said, so myself, Ravi, I'm working at GE Vernova as a carbon capture integration leader. And if I go into my first slide, okay. So as we just talked about, there are multiple challenges with the carbon capture, especially the post-combustion carbon capture. And if you drill down to the top two, we have the technical challenges and then we have the economical. When I talk about the technical challenges, as also Ankit mentioned about, we have energy requirements. We are talking about 3 gigajoules of energy per ton of CO2 capture, which is humongous and which we need to tackle. And the second is economical. The cost of, it's always heard, right? The carbon capture is expensive. So somewhere we have to address these two challenges if we have to implement more plants, the more carbon capture one, and that's how we are working around on it. So before going into the exact solutions, I'll try to touch base on what the the breakdown of the problem. So if you look at the left side, we have the typical capex breakdown for a combined cycle power plant with a carbon capture. And as you can observe, right, it is around 44% of the cost is going into the absorption system, and 12.2% to the pre-scrubber. So almost more than half of it is going into the pre-processing in the absorption and the pre-cooling. And so anything we are going to capture, anything we are going to address in these two areas is going to have a considerable impact on the capex of the carbon capture plant. And comes to the right side, that is about the power requirement. And as you can see, almost 60% of energy requirement is going into the reboiler. That is a specific reboiler duty which I was talking about, anywhere from 2.5 to 3 gigajoules of per ton of CO2 captured. So if you are trying to have any options, any technology or any innovation which is going to cover the left and right side, reducing the size of the absorber or reducing the energy requirement, that is fundamentally is going to address the problem of carbon capture for the NGCCs. So now comes to what's our solutions. At G1 Nova, we are offering the solutions of integrated NGCC CCS solutions. And if you are looking at the top left corner, the steam integration, it's all about combining the combined cycle power plant with the carbon capture. So there is no independent plants. It's about combining the both plants, make use of all the energy availability so that we can reduce the energy requirements and increase the overall performance. Second one is the EGR, exhaust gas recirculation, which I'm going to talk a little more detail, but it's all about reusing the exhaust gases back to the gas turbine so that increasing the CO2 concentration, thereby reducing the energy requirement and also reducing the size of the carbon capture plant. So there are other solutions like equipment upgrades and control system. Interest of time, I'm not going to cover other two topics, but let's dive into the first two, the steam integration and the exhaust gas recirculation here. So the exhaust gas recirculation, as the name suggests, right, it's about recirculating the exhaust gases back to the gas turbine. So if you see the top left one, a traditional combined cycle power plant, gas-based power plant, it has gas turbine and the HRSG and the generator and the steam turbine. Now, if you are adding the EGR as a loop, which you can see the top left bottom, we are adding the EGR loop where we are taking a percentage of exhaust gases, cool it, condition it, and send it back to the gas turbine. So that's where we are calling it as a recirculation. So what are the advantages of doing this recirculation? And before getting into that, we will not take the whole gases, obviously. We will take some percentage. That percentage varies from 30 to 40% based upon the frame and project and the site requirement. So 30% of exhaust gases we are sending back to the gas turbine. So by doing that, so as you can see the summary here, we are reducing the flue gas flow to the carbon capture. So that is going to reduce the size of the carbon capture plant, reducing the footprint. And additionally, we are increasing the CO2 concentration. So the gas turbine exhaust has anywhere from 3.8 to 4% of the CO2. By recirculating, we are increasing the CO2 concentration by anywhere from 50 to 60%. So that CO2 concentration will reach anywhere from 7.2 to 7.5%. So this will have multiple impact. As you can see, absorber size is going to be reduced. Now we have a concentrated CO2 and we have a smaller exhaust flow. The volumetric flow is reduced because 30% is going back to the gas turbine. And obviously this is going to have a considerable impact on the SRD, specific reboiler duty. And as you know, as per the Gibbs-free energy, if you have more CO2 concentration, it is easy to capture it, then we need less amount of heat required to capture the CO2. So now these are more on the technical aspects of it, and as I mentioned at the beginning of this slide, so how it is going to impact the plant and how it's going to benefit the customer. So this is going to reduce the capex and the opex. So I'll go a little more details how it's impacting the capex and opex, but fundamentally, as you can see, so we are reducing the volumetric flow by 30%, then subsequently, theoretically 30% of reduction in the cost, it not the practical, but we are talking about almost 20% reduction in the capex. And by increasing the CO2 concentration, we are reducing the oxygen concentration. So then that is going to have less oxidation of the solvent, then that is going to improve the life of the solvents, then there is a reduction in the OPEX. So that's how the impact on the CAPEX and OPEX. So we are going to have a smaller absorber, and we are going to eliminate the external auxiliary boiler. We are going to have slightly smaller regenerator. These are going to turn down to reduction in the CCUS footprint, I mean the land required to set up the carbon capture plant. So again, before moving on to the next slide, so I just want to highlight that EGR is not something very new. It's a TRL7 kind of technology, TRL7-8. It's been quite effectively used for reduction in the NOx in the early 2000s, and now it is repurposed for the increasing the CO2 concentration. Now, if you go into the second topic on the steam integration, so as I mentioned, we need around 2.8 or 3 gigajoules of heat per ton of CO2 capture, and that in a traditional carbon capture plant, that steam comes from the auxiliary boiler. But the challenge here is auxiliary boiler also emits the flue gases, then we have to capture it. So to capture the CO2, we are adding additional CO2 because of the auxiliary boiler, and that size of the plant is increases anywhere from 10 to 15% just because of the auxiliary boiler. So what we are trying to do here is combining the steam turbine and taking the extraction from the steam turbine, using it for the process that by far eliminates the auxiliary boiler, so additional flue gases to the carbon capture plant, and also improves the overall efficiency of the plant. Now, the problem is not about taking the steam from the steam turbine, but we need to make sure that it is not deteriorating the overall performance of the combined cycle power plant. So as you can see, there are 5 options are there. I mean, there are infinite options to take the steam from the steam turbine, but if you look at aim of reducing the impact on performance, there are 5 major points where you can take the steam from the steam turbine, which is just highlighted here. But again, if you are taking it from low pressure, that is more preferable option, so that we are using the steam which has pretty much completed all the work. So we are talking about reducing the pressure and the temperature from 150 bar to 6 bar. That is what needed for the carbon capture one. So using this low pressure and temperature steam is going to be beneficial, that it's reduce the impact on the performance. However, we can take it from the high pressure, intermediate pressure, but obviously that have a significant impact on the performance of the overall plant. So just to re-highlight the same thing which I mentioned here, by adding the steam extraction from the steam turbine instead of the auxiliary boiler, not only eliminates the auxiliary boiler, that is the capex impact, it also reduces the overall flue gases which is needed for the carbon capture. So that reduces the capex of the carbon capture plant, and also it improves the overall performance. I'm going to throw some numbers and how it's going to looks like, but just for re-highlighting purpose. Okay, now comes to the numbers. So how overall performance is going to be impacted because of the EGR, purely because of the EGR. You can see from the top left side, no EGR. By the time we add the EGR, we are seeing that there is a bypass loop taking the 30% of exhaust gases back to the gas turbine. So as you can understand, right? So exhaust gases are high heat. We are talking about 120 C, and that we cannot directly send it back to the gas turbine. That need to be conditioned. But despite of that, the temperature of the 30% of flow is slightly more than the ambient. That increases the overall temperature inlet for the gas turbine. That would slightly reduces the gas turbine performance. But despite of that, there is a slight reduction in the gas turbine performance, but there is a huge impact in the increase in the steam turbine performance that cumulatively improves the overall combined cycle efficiency. That you can see here on the top right graph. As you are increasing the EGR ratio, if you are going from 30 to 40% of EGR ratio, there is a NGCC's output is increasing by 4%. And 4% is a gigantic number. We are talking about 1000 megawatt plant, which I'm going to show some actual plants we are working on it, but this number is huge. And these are the things directly going to improve the performance, and that is fundamentally is going to help the customer. They're going to generate more power and make more money out of it. And comes to the OPEX one, as we are increasing the CO2 concentration, EGR ratio, we are increasing the more CO2 concentration, which you can see the bottom left graph, as EGR ratio increases, we are increasing the CO2 concentration. Again, back to the concept of Gibbs free energy, more CO2 concentration, easy to capture. And the right side is increasing the CO2 concentration, reduce the oxygen, that improves the life of solvent. So we are talking about increasing the life of solvent, then reducing the OPEX of the carbon capture plant. Now, next to the steam turbine integration, so it's about, I'm trying to make it simple in interest of time. As we are doing the integration, we are eliminating the auxiliary boiler, which I mentioned multiple times, and we're using the steam from the steam turbine. So that you can see in the bottom left corner, the graph, the bar chart shows just from the bolt-on solution without EGR, without steam integration, there's a performance drop by almost 63 to 42%. It's a huge drop in the performance. But by adding the steam integration, we are able to gain approximately 13% of efficiency back. So that's the impact of the steam integration, which I'm going to give you a cumulative impact of the EGR and the steam integration. But the steam turbine integration, which is kind of crucial, which enhances the overall performance and also reduces the capex and the opex. So this slide summarizes the cumulative impact of the EGR, exhaust gas recirculation, and the steam. Again, I'm bringing the same slide which I showed in the first slide. If you see, the around 44% of capex is going into the absorption system. And by targeting on the absorption system, by reducing the size of absorption and the steam requirement, we could able to reduce the capex from almost 37%, which you can see. And the impact of only EGR is falls around 5 to 8% on the total plant cost. Now, so far I'm talking about the technology, but fundamentally everything works well only if that can be commercialized. And so these are the commercial plants which I'm talking about. The first one is world's first commercial scale NGCC CCS project. And we are talking about 2 million tons per annum of capacity. It's an 860 megawatt plant. It's a HA mission. And it's a FID is completed. The construction is going to be started in the mid of this year. And the two technologies which I talked, the steam integration and EGR, are going to be implemented in this project. And the second one is on the Alabama Power. It's a DOE, Department of Energy, US funded FEED study. And you can see the EGR loops here. And again, this is a gigantic study. We're talking about 1.6 million tons per annum of capture. And we could able to attain a break-even cost of $100 per ton. Yeah. Okay, so I'm going to cover on the last slide just to summarize what I've been mentioning about. So reducing the cost of carbon capture is very, very important because it's going to enhance the adoption. That is what we are looking for. And EGR steam integration is going to address this very precisely. And we are, just to summarize, it has a capability to reduce the capex by 20% and efficiency by 5%. And as I mentioned, these are implementing in the world's first NGC CCS project at the Net Zero T site. So that's all from my side. If you have any questions, you can reach out to me probably right after this presentation. Thank you.
Thanks, Ravi. Thanks. Now, may I request Mr. Sivdeep Gagat to make his presentation. He leads the industrial solutions for Siemens Digital and has good experience of working with the asset-heavy industries. So, and he would be making a presentation on leveraging AI, computer modeling, digital twins like emerging technologies for CO2 capture. So, please.
Thank you. Can you hear me?
Please.
Yeah, all right. So, very good morning to everyone. Sorry, I was a little bit late to the panel. The cab got stuck in a traffic jam, so apologies for being late to the panelists. So, good morning. My name is Shivdeep. I'm normally based in Berlin. Very happy to be here at the India Energy Week. Just a raise of hands. How many of you here think that Siemens is making gas turbines?
Most of the people.
How many of you think that Siemens is making automation software and hardware? Okay. And how many of you know that Siemens also has new solutions on computational fluid dynamics, systems modeling, CAD, and all of that? Okay, very few. So just to put those things in perspective, I'm from the part of Siemens, so I'll just maybe start sharing. So I'm from the part of Siemens that is coming recently into the Siemens family, which is basically through acquisitions of companies like CD Adapco, Mentor Graphics. So companies that have come up in the last 10 to 20 years with the expertise in the solution domains of computational technologies for modeling, simulation, optimization across domains and across multi-physics and multi-scale systems. So really, there's a very strong play that we have in the energy sector. And today I'll show some of the use cases that we have done with our customers, but also highlight certain reasons why this technology is key to problems that we face in the field, especially like going what Ravi was mentioning, especially on the power plant side with GE and what was done here before. So a lot of those things, new technologies like rotating packed bed reactors, things that are being used in the industry, they require a very strong physics background, and that's where we come in, both on optimizing the CapEx, front-end design, but while you're doing that, early in the project, also enabling you to really also look at the life cycle cost of a design. So not just one, but taking it more holistically. So going by the in the market, what we see is typically that these are the four key drivers of what is happening. The energy efficiency, we have aging assets, so things and plants that were built 50 years ago, over a period of time, things have been added, life extension of those plants, remaining useful life, retrofitting those plants with new requirements, carbon capture being one of them. Time to market for these solutions that need to be getting there very quickly. And while we do that, we need to be sustainable, and the demand that is continuous in increase, especially with the new AI technologies coming in. One Google search versus one ChatGPT search is almost 10x the factor of energy. Forget DeepSeek, that's a different topic. But yeah, overall, what we see is that the simplest back to the basic solutions are really something that is very low risk. The return on investment is quite high. So that's why the technologies that we're offering, basically that include modeling and simulation, are being picked up a lot in the market. And what we're trying to do from our side is really make these technologies more accessible, more fast, and more scalable and accurate. So what do I mean by that? So what we're trying to do is, so those of you who are familiar with the modeling and simulation world, and especially the more detailed you go, let's say with computational fluid dynamics, the time to solution increases. So we have calculations that could take months, it could take weeks, it could run on 100 clusters. Now what we're trying to do is implement certain technologies that can reduce that time and really make it fireable at the pace at which a PLC can fire. So I'll show you some examples, and that's where we combine some path-breaking technologies with machine learning, with systems, with computational fluid dynamics, and we cross different scales, integrate that, reduce that complexity, and make it accessible to someone who's using it in operations. And I'll show some examples. So currently, in most of the plants we see, the word digital twin has a very different definition depending on where you're coming from. So level 1 would be a simplified, let's say, SCADA. You have a plant, you instrument it, you have that instrumentation visualized in a screen. Level 2 would be when you apply certain techniques to that data, whether your sensors are off, are you having a drift in your data? So data validation, reconciliation, that would be level 2. Level 3 is where we start seeing things that are coming up with AI. And where it's very easy to throw AI at bad data, and there will always be gaps. And your plant, let's say if you're operating a very high sensitivity equipment, it's not a laboratory. So a lot of data, new paths to failure, the way it has not operated before, those are things that are not predictable based on the data that is already there. Second, even with with this data in mind, the root cause of certain process subsets is something that is still causing a lot of problems. So, just purely an AI and data-driven approach will have its limitation very soon. And that's why what we want to do is augment all of this with technologies that we call executable digital twins. And executable digital twins is simply a model, a physics-based first principles model that is then brought down into an operational framework, hiding the complexity of it, and making it accessible to someone who's doing operations on the plant without any additional training, embedding that into hardware, into the Siemens automation side, and then sort of taking that view to the value. And if I look at what are the gaps we are fulfilling through that, is that your plant it has limited instrumentation. So if you, let's say, have a pump that you get from company A, it's certified for 20 degrees water. Now you want to use the same pump for, let's say, liquid ammonia or some other hydrocarbon at different viscosity, density. So that should be stayed especially at off-rated points. That is something that is not very obvious to understand, especially if we have certified on a certain point. And from that point of view, when it comes to equipment that is often not operated as the standard point, the information on what it should be doing becomes difficult to understand. So that's where we complement the reference health, new operating state. So let's say if you are running at a state where you haven't run before, so you can't predict that information. All kinds of noise and vibration issues. And I'm specifically saying that is because in this industry, my experience is, and feel free to disagree with me afterwards, a lot of things are also over-designed, and that gives us a very strong potential for carbon reduction. And second, when we have a lot of focus on the process side of things, but the mechanical side is often neglected. So compressors, pumps, valves, the actuation of these things. And that the simple answer is that there are tools in the market that do process simulation, but there's another side of it which they neglect, which is momentum conservation. So when you're sort of, let's say, doing a simulation on a process tool, it's kind of giving you, let's say, feed input changes, different concentrations, what you get as an output. But well, let's say if you have 5 lines open at the same time, what happens? If you turn a pump on, what is that ramp up like? How long do you have until you get on spec with your production? So those kind of things that require a different kind of a technology. Closed mass balance is something that this industry struggles with. And the answer is not specifically on the process side, because to run a calculation there, you would start with a closed mass balance. A momentum-based solution actually gives you a closed mass balance as an output. So those kind of things we can specifically address through our systems. And there's a whole range of things that apply not just to carbon capture, but overall, all the way from pipelines and facilities, specifically to machinery and equipment, going through different kind of scenarios. So let's say you want to look at steady states, surging, choking, and with carbon dioxide, it's even more strict because it has certain requirements, especially when it comes to the supercriticality of it. And we have done some work with some of our customers. I'll come to that later. Looking at even emergency scenarios. So let's say if you have 5 pumps feeding a system and all of them go offline at the same point, and the redundancy comes up. So what's the worst can you expect? How do you mitigate those things? A lot of things that happen in the plant can be then quite quickly understood. So just to give you an example here is a desulfurizer. So basically it's the same process you could use for carbon dioxide. And what we're looking at the physical effects of different multi-phase flow for absorption, the neutralization reactants, and the different time scales, and really at the concept stage. So really if you're designing these equipments or you're modifying it, that's one thing. But if you're also looking at different flow rates, different slurry concentrations, that also can give you a very quick answer to what you can expect as a yield, how much fouling would you expect, what is the let's say the outlet stream, the concentrations, and so on. And just to give you an example of this, so this example is a full fidelity model that we have run, let's say with the CFD solver. Now we have techniques to actually get it real time, and what I'm showing you here is actually something which we call a ROM. A ROM stands for a reduced order model. And what we have done is taken that CFD, about 200K degrees of freedom, got it down to about 8 degrees of freedom with the mathematics of state space. And we put that into a visualization. So really what you're looking at is one of these mixes running real time, and the other one is sort of mimicking that behavior with that operating point. And to give you an example, this is not just to show that there is a cool technology behind it, but there's a purpose to it. And what we have here is just an example where you have an application that is programmed using one of our low-code solutions, which is called Mendix, again, the new acquisition. And through that, you can deploy very easily code new applications and make these really nice technologies deployable to someone who doesn't have time to understand or take time to learn a new tool, but very focused on what they need to do. So really, this is really a Mendix-based application, and what you see here is simply, let's say it's a mixer, and they get a new batch of ingredients, and depending on the particle size, what are your yields like, where is your holdup, are you getting the right mix, how long is your residence time, what do you need to do to make sure that what you get in the end stays on spec. So it's really to help the operators to understand and use these solutions really in real time. We talked about steam, steam being one of the key concerns here as well with the power generation side and the renewable carbon capture. And so basically, this is an example where we had BASF in Antwerpen. I cannot talk about a lot of things that were done because they are confidential in nature. But one of the things they implemented was basically the whole plant wide. It's a 25 square kilometer facility, and they had a digital twin which is completely based on the physics, showing them exactly what the condensate rate is and where is it forming, and things like process upsets. So let's say they had on the different days they had the same demand, but on one day they had more condensate arriving, the other day there was not. So it was clearly a process upset. In the past, what would have happened is someone would have taken it offline, seen what's happened. If they figured it out, otherwise things move on, we don't have time. In this case, it was very clear. What happened was the routing the steam took in that day was different. So it came from a different unit as compared to where it normally comes from. And since it had to travel a longer distance, you can expect a higher pressure drop. So more condensate actually eventually coming up. And this is something it is very difficult to catch with instrumentation, because instrumentation just gives you a small time picture. It takes you just some measurement points, and this basically complements all of that sensor information and updates that to an as-operated state every 5 minutes as it stays in an automation loop. And all of this complexity is hidden. We have then further on worked with a lot of gas supply companies in Germany. So the case here I'm sharing is from a company called Open Grid Europe. And Open Grid is the gas supplier, natural gas supplier for Germany. And the critical question for them is, how do they integrate carbon dioxide? How do they integrate hydrogen and other fuel products, new products that are coming into the system? And one of the key concerns is the current, given modeling tools, the equation of states are quite limited. So with hydrogen especially, and also with the supercriticality of CO2, things that have worked until now are not as accurate. So therefore, they have to go for a new solution, which captures not just the thermodynamics, but also the thermodynamics coupled with momentum transfer. That is something that we have done together with it. You can have a look at the QR code and find the whole study. And this allows them to not just map the CO2 and make sure that it is staying in that supercritical phase, but also look at other aspects like compression, even co-compression of hydrogen through other chemicals. Right. Yeah. And so I'll close with this. Basically, just to show that there are these technologies, and there's a lot they can offer, both from the operationals point of view as well as design. And we are constantly working with our customers, with our partners, to make these technologies more accessible and have them bring more value to the industry, to have a more sustainable and strong energy future everywhere. Right. Thank you, everyone, for your attention. And yeah, that's it. I'll close my.
Thank you so much, Samir. Thank you. And now may I request Mr. Samir Bhirmani, who is GM Sustainability GAIL, has worked with GAIL about 31 years, has experience of across the value chain of natural gas, and has worked with few petrochemical plants also like Vijaypur, Pata and others. And he would be talking about to us on SAF, which is one of the most prominent CO2 polarization approach today. So over to you.
Presentation on SAF, which is basically one of the key CO2 validation technology, which is driving GAIL's net zero ambitions. And this presentation will be jointly delivered by me and my colleague Vikas, who is right here in front of me. So just move forward. So these are the main topics we'll be covering: the growing demand of aviation turbine fuel in the current context, India's aviation growth journey, and what is SAF, government policies on SAF, milestone SAF flights which have been
Good
taken.
morning, ladies and gentlemen. We welcome you to third edition of IEW 2025. The show timings for today are from 10 a.m. to 6 p.m. Please take care of your belongings. Thank you.
Various challenges and opportunities being faced for the net zero journeys that various companies are following, and India's potential in SAF development and conclusions. So this slide shows the growing air travel, which is increasing by almost 6% on an annual basis, and corresponding to that, the requirement of jet fuel has also increased, which is around 450 million kiloliters currently. So the India's airline industry is also increasing, with the passenger traffic increasing to 154 million. That was the last year's figures. Currently, it is around 165, and India's demand for ATF is around 8.3 million tons. And this has happened because of the improved infrastructure, the rising disposable incomes which are available with the people in India, and growing travel by air mode. So now the question is, why sustainable aviation fuel? So sustainable aviation fuel is basically a non-fossil derived fuel, which is just a drop-in fuel as compared to ATF. And the global estimated SAF production capacity is estimated to be around 20 million tons per year. The growing travel, which is growing every 5% annually, there is a need for SAF in the coming years. SAF reduces the environmental impact, wherein the life cycle savings on CO2 emissions are to the tune of 80%. SAF is a safe and chemically identical to traditional ATF, and the International Civil Aviation Organizations, which is running a program called CORSIA, that is Carbon Offsetting and Reduction Scheme for International Aviation. It aims to reduce the CO2 emissions for the countries. Now, this program is basically like in 3 phases. The pilot phase was for 4 years, that is from 21 to 23, and there was a voluntary phase which is going on 24 to 26, and there is a mandatory second phase wherein certain quantities of SAF blending will be mandatory. Blending of SAF in ATF. And as of now, 129 countries have participated to be members of this CORSIA program, which includes leading countries like United States, China, Canada, UK. India is also a participant to this. And there are various government policies. Recently, during the G20 summit, which was held in 2023, there was a global biofuel alliance which was formed, and more than 20 countries are participant to this. India is also a participant to the CORSIA program, and the indicative blending targets which are for India are like 1% SAF blending by 2027 and 2% SAF blending by 2028, and by 2030 this is supposed to increase to 5%. And this blending will be for international flights which will be landing in India. So India is also aiming to produce SAF locally and contribute towards global net zero emissions. Now, these are the various aviation like technologies which are available for production of SAF. The first one is HEFA, which is hydroprocessed esters and fatty acids, basically the used cooking oils, which is used to produce SAF. And then there is a second Fischer-Tropsch process, which is also a very old technology, way back in 2025, which is breaking carbon-containing materials into synthetic gas. The new technologies which are developing these days are alcohol to jet, wherein bioethanol is getting converted to SAF. And another is the power to liquid, wherein also we are producing SAF to this mode.
Good morning, everybody. Myself Vikas Kumar, working with GAIL India Limited. What Virmani sir told is alcohol to jet. For the alcohol to jet, there are two methodology. One is from ethanol to Z and other is methanol to Z. Ethanol to Z is technically more mature. It is at TRL 8 to 9, but methanol to Z is around 6 to 7 TRL level. In ethanol to Z, the production process is like from ethanol to first we have to make ethylene and then from ethynyl to Z. And in the major raw material for ethylene to Z is hydrogen and renewable energy. So these are the milestones for SAF. The SAF is being used as drop-in fuel in aviation turbines since 2018, and the most accomplished achievement is in December 2023 when Virgin Atlantic used a flight from London to New York based on 100% SAF. So that is a great achievement. And from there on, we can think of using more SAF as an alternate to aviation turbine fuel. These are the leading technology provider for SAF. In India, CSIR IIP is developing indigenous single-step catalytic technology for SAF production. At world level, there are so many companies which are in SAF business like LanzaJet, Technip, Pras, Metafuels, Lummus, and some more companies are also there. Now, how GAIL is aligned with SAF. For the SAF, basically we need three basic building blocks. One is CO2, second is green hydrogen, and third is renewable energy. For production of 1 kg of SAF at commercial scale plant, we need around 6 units of electricity and around half kg of green hydrogen. So as far as GAIL is concerned, we are having CO2 in abundance. The thing is, as far as GAIL is concerned, we are lucky that for CO2 recovery, we do not need any further investment. We are already getting CO2 from domestic gas sourcing, which is around 4 to 5%. And as a byproduct, prior to processing of this gas, we need to remove CO2. So CO2 is already removed from GAIL processes, and we are not needing any further investment for CO2 recovery. So feedstock is available with GAIL. Green hydrogen, we have already running the 4.3 TPD plant at Bijapur, and we are exploring opportunities for enhancing this green hydrogen capacity by more than 30 times from the present capacity, which is 4.3 TPD. Renewable energy, we are already generating 135 megawatt, and we are exploring to reach more than 3 gigawatt by 2030. And by having CO2, by having green hydrogen, and by having renewable energy, we are best positioned for aligning with SAF production. The benefits of SAF are a lot many. The first and foremost benefit is it reduces GHG emission by 80%. It also reduces particulate matters and SOx, which improves the air quality. For SAF, basically most of the SAF being produced right now is HEFA based, but since HEFA is limited, the used cooking oil has a limitation, so we need to have SAF based on CO2. Further, if we are using SAF, it will reduce our dependence on imported crudes, and it will save the foreign exchange. But there are challenges also associated with SAF adaptation. The most important challenge is the cost of production. The production of SAF based on different technology is 2 to 5 times higher than the conventional cost. The cheapest production technology is available based on HEFA, which is worldwide used, and the highest cost we are getting in power to liquid process. In power to liquid, actually what happens, power to liquid basically is a carbon negative technology. We are taking direct carbon from the atmosphere and then we are using it for the production of SAF. So if we use power to liquid, it will be a carbon negative thing. The second is feedstock availability. We are already having sustainable sourcing. The infrastructure is a big challenge because nowadays still we are very slow in production of SAF and there is a huge mandate for SAF because of the CORSIA and all. As Brimani sir already said that India is a participant to this CORSIA and we have to go for 1% SAF blending by 2027, which shall increase to 2% by 2028. Policy support is also required for adaptation of SAF technology. Opportunities is abundant because the benefits are a great, so 80% emission reduction, 17.3 million ton market growth, global SAF production is expected to reach by 2030, 17.3 million ton. So it is, the best part is SAF is a drop-in fuel, as Birmani sir already told, it is a drop-in fuel to aviation turbine fuel and we can use SAF in any ratio right from 0.1 to 100%. In the existing aviation turbine planes without any modification. That is the best thing. India's potential, because of greater population and aviation demand, India has a growing aviation market. So the aviation turbine fuel consumption will increase and so is the consumption of SAF. The blending target, as already we have told, technological innovation we are doing. So many companies are involved in development of SAF technology. Feedstock is abundant in India. Agricultural residue is also one of the major feedstock other than used cooking oil. As a conclusion, we can see that SAF is very critical for decarbonization because it accounts for around 2% of global CO2 emission. But the thing is, technological advancement is required and a very good collaborative effort is required to increase the SAF production. But before I conclude, let me share a small story. There was a man along with his family stuck in a desert and badly needing water. So the man asked his family member to wait and went in search of water. On the way, he met a saint who guided him to the source. And while coming back with the water, he found a group of people who were very thirsty. So he gave his water to them and went again for to fetch the water for second time. The second time the same happens. During the third time, the saint again appeared and said, "Why you are giving your water to them? Instead, you show them the way as I showed you." So, my dear friends, the net zero responsibility is huge. It can't be achieved unless otherwise we empower all individual, all companies, and all countries. So, jointly only we can achieve this, and for this we need to empower one and all. Thank you. Thank you, my dear.
Thank you so much, Mr. Vinwani and Vikas. And I have no time left for queries, so please feel free. All of us are available outside this room, so please feel free to connect up with any one of us if you have any query. And I moderated a similar panel last year, and with these presentations, I see the technology has matured a bit and efficiency has increased. And which was seemingly 2 years back looking to be a big trouble, now it is in the horizons and we see the solutions are available here. So with that, I would like to conclude the session and hand over to the organizers. Thank you very much, ladies and gentlemen.